All right, so in this video, we're just going to kind of quickly prove that integration, the technique of integration by parts actually works now that we have the fundamental theorem, the first fundamental theorem of calculus. It's easy to prove this. So this is theorem 34.2. So if U and V are continuous on AB, differentiable on the open interval AB, and U prime and V prime are integrable on AB, then, well, the way they write it is like this. So the integral from A to B of U V prime plus the integral from A to B of U prime V equals U of B, V of B minus U of A, V of A, right? And when it's written suggestively like this, it's kind of obvious, what the proof is going to be, which is literally just that, the derivative of UV is UV prime plus U prime V, right? So, we can easily recognize the left-hand side as the integral of the derivative of UV and then use the fundamental theorem of calculus. That's basically what happens. But of course, you're probably more familiar with seeing this, seeing the equation written with like, one of these terms moved to the other side. So like something like the integral of UV prime from A to B equals UV, and I'm going to write this notation, UV evaluated at B minus UV evaluated at A minus the integral from A to B of U prime V, right? So that's kind of the familiar phrasing of integration by parts. So the proof is just, right, so given U and V, take G equals UV. Then G prime is U prime V plus UV prime, right, by the product rule, which we proved, right? So by the fundamental theorem of calculus 1, the integral from A to B of G prime is G of B minus G of A, right? And so on this side, since G is just UV, this is U of B, V of B minus U of A, V of A, right? And then on this side, by linearity, right? This equals, well, so we have the expression, so this is the integral from A to B of U prime V plus UV prime, which equals, so linearity really is applying in this second step here, the integral from A to B of U prime V plus the integral from A to B of UV prime. And so this is by linearity, right? And yeah, that's it. Right, and this is just a useful computational technique. You've all seen integration by parts before. We can use it, so they give an example. We can use it to integrate things like, okay, the integral from 0 to pi of x cosine of x dx, right? This should be, if we recognize cosine as the derivative of sine, this is going to be x sine of x evaluated at pi and 0 minus the integral of just sine of x from 0 to pi dx, right? And so sine of pi is 0, and right, and sine of 0 is 0, so this term is just 0. And then this is, so negative cosine of x is the integral of sine of x, right? Evaluated at pi and 0. So this is cosine of pi minus cosine of 0. So this is negative 1 minus 1. And this is negative 2, right? So it's just a handy, I mean, yeah, like I said, I'm sure you've all seen it before, but it's nice that we can now use this, right? We can use this theorem without much fanfare, right? I mean, if you just know that the integral takes this form for two, continuous and differentiable functions whose derivatives are integrable, then you can just automatically apply this theorem without a lot of work. So yeah, that's integration by parts. And so, we basically just got that from the fundamental theorem, really. Yeah. So in the next video, we'll prove the other fundamental theorem, which sort of goes in the opposite direction, where we're differentiating an integral.